Okay, so thank you for the invitation to give an introduction to cosmological relaxation models. So I'll try to keep it pedagogical, and I'll start really with the motivation for why we should think about the hierarchy problem seriously, even more now than before. So I'll spend a bit of time motivating cosmological relaxation and give an introduction to the basic mechanism. And then I'll talk about the models which I find the most promising, which are the ones with particle production. So electroweak symmetry breaking is, in principle, realizable in many different ways in nature, and it's kind of surprising to think that we have just a standard model Higgs to the extent that we've measured it. And in principle, there could have been all kinds of ways of breaking electroweak symmetry, from strongly coupled models to pseudo-Goldstone bosons from strongly coupled sectors to a Higgs with SUSY, to many different possibilities. But there is a tension between the simplicity of the electroweak symmetry breaking sector and naturalness. So the naturalness issue is essentially tied to the well-known fact that fundamental scalars have quadratic corrections to their masses proportional to the heavy scale of new physics. And this is a feature which is in any scalar theory that isn't protected by some additional mechanism. And it's not inconsistent to have this issue. It's just that it's not attractive in the same sense that in the very earliest example I could think of, we have a problem with the inertial charge being equal to the charge of gravity. So the inertial mass and the charge of gravity in the classical Newtonian framework have nothing to do with each other, yet it's not inconsistent to set them equal, but we just go out and measure it, and it just happens that they're always equal to the inertial mass. So this sort of screams for a deeper explanation, and there are many other features that also require these sort of explanations of fine-tuning, for which we have a deeper principle. So the Higgs has a similar argument, and we expect new physics close to the weak scale based on this argument. And usually I would leave it at that, but recently there's been a lot of misconceptions about this problem, which is maybe under debate given that we haven't seen new physics at the weak scale. So I really want to emphasize that, yes, the standard model doesn't have a fine-tuning problem, but the standard model does not explain the origin of electroweak symmetry breaking. And the problem of fine-tuning is really tied to understanding the origin of electroweak symmetry breaking. So by understanding, I mean that if you have an arbitrary feature that you just put in by hand, and there's no other reason than that's just what it is, then you might accept that, or you might try and think of some explanation, just like the equivalence principle explains the equality of the inertial mass and charges. So by an explanation, we mean that something will generate the Higgs mass in a calculable way, and it's really when you have a calculable Higgs mass that you get the problem with this correction to its quadratic term. So unlike the solutions to these other problems that we see here, like the pattern of the Yukawa couplings, the QCD theta term, and neutrino masses, and so on, if you have an explanation for the origin of electroweak symmetry breaking, you have a fine-tuning problem, because we have no theories where you calculate the Higgs mass, and you can decouple new physics in a natural way. So this is a very concrete problem, especially given that we haven't seen anything yet at the weak scale. So the moods of theorists have shifted in a very up and down way, and it seems like the story at the LHC might be that we don't have physics at the weak scale. So it's interesting to think that there may be cosmological dynamics that is responsible for decoupling new physics in a natural way, where we don't give up on having an origin for the Higgs sector, but maybe we just have a cosmological part of the story. So this is the mechanism that was proposed a few years ago by Graham, Kaplan, and Rajendran. And this mechanism got a lot of attention because it is a new approach, essentially, to this problem. The Higgs mass in this model is naturally at a large cutoff m. So in these theories, you say that the cutoff is at some high scale. Let's say it's at 10 to the 6 GeV or something like that. And the Higgs mass is natural. But the reason why the weak scale is what it is because you have an axion-like particle where, unlike the axions that you have heard about so far, the axion's shift symmetry is broken by a small parameter g. So the small parameter g parameterizes a soft breaking of the shift symmetry, and if you write down all the possible terms that are induced by this shift symmetry breaking term, then you get a series of terms proportional to g. And this allows the axion to scan an effective Higgs mass. So it couples to the Higgs mass squared, and that term there gives it a rolling slope. So the GM squared A term basically gives you the slope, and if the relaxion in the early universe is somehow starting at a displaced field value, then you can see that as it's rolling, it scans the Higgs mass from a positive value, where the Higgs vacuum expectation value is 0, and as it rolls past a critical point, the Higgs vacuum expectation value switches on as the Higgs mass turns negative. So how does this explain the weak scale? Well, you need a natural way for it to stop soon after the Higgs vacuum expectation value switches on. And this is essentially the axion's periodic potential, which is proportional to the Higgs VEV. So this periodic potential barrier could be, like in the QCD axion, responsible for the dependence on the Higgs vacuum expectation value. For the QCD axion, this would be the pion mass, for example. So this mechanism is a sort of reinterpretation of a model by Abbott, which was used to solve the cosmological constant in a certain way. Just the backreaction mechanism, in this case, depends on the weak scale, so it's readapted as a solution to the weak scale hierarchy problem. So the trapping happens when the barriers grow to the point where they can compensate for the slow roll slope. And this is the condition that sets the weak scale when the slope is equal to the periodic potential barrier. And you can see there that we can have a scale V much less than m for a technically natural choice of the parameter g. So the problem with these mechanisms is, in the original formulation, is that you have to have Hubble, for example, being less than the weak scale, otherwise you're not scanning the zero temperature potential. So Hubble has to be less than 10 to the minus 8 GeV during inflation, which is a very, very low scale of inflation. And the fact that the Hubble scale is so low means that the slope is also very flat. So G has to have a value of, say, 10 to the minus 30 GeV. So such a small value is technically natural. When you switch G to 0, then the shift symmetry is restored. So it's technically natural for it to be very small, but it's not very attractive to put in a value like that by hand, and you get into all sorts of problems with the weak gravity conjecture and so on. And then the problem as well with having such a flat slope is that if this happens during inflation, the number of e-folds is exponentially large. So we're talking 10 to the 30 exponential e-foldings. So this mechanism is a nice proof of concept, but there are all kinds of issues with actually realizing it. However, I believe that cosmological relaxation with particle production solves a lot of these issues. So the original mechanism was maybe dismissed a bit prematurely on the basis of these strange features, but we can generalize these models by saying that, well, the problem with the original model is that the periodic potential barriers depend on the Higgs vacuum expectation value linearly. So if this is the QCD axion, you can think of the QCD condensate, and then the pion masses has a linear dependence on the Higgs VEV, and when you have the confinement scale, you break the electroweak symmetry, and that's why it depends on V. But if you have the QCD axion, then this no longer is a solution to the theta problem, and you violate CP badly. So then you need to have a new gauge group G, but because it depends on the Higgs VEV linearly, it also has to break electroweak symmetry, so your new gauge group also has to be close to the weak scale. So now you're reintroducing new physics of the weak scale, and it's no longer doing what you originally wanted to do. And you also have to sort of put this new gauge group in close to the weak scale for no reason, so you have a coincidence problem, so to speak. So this paper by Espinosa et al. Proposed solving this coincidence problem by having a new gauge group that quadratically depends on the Higgs VEV, so it no longer breaks electroweak symmetry when it confines. So then they said that you could decouple this to any higher scale you want, and this fixes all the problems of the original n=1 models, and you can have a higher cutoff. The cost of doing this is that you have barriers that stop the relaxon from rolling right from the beginning. So they have to add a second scalar to relax the relaxion to allow the relaxion to do its job. So they say themselves this is just another proof of concept that you can make this work at higher scales without having any new physics below the cutoff. but having a double scanning mechanism seems to just make it even more contrived. So for a while there was a lot of phenomenological papers and so on, but the general consensus seemed to be that these models were a bit too contrived, if a nice idea. However, the n=0 model is basically saying that the periodic potential barriers don't have to depend on the Higgs Vev at all. If you think of cosmological relaxation as a more general mechanism where you just have some Higgs-dependent phenomena that stops a relaxon from molding, it doesn't have to be in the potential barriers. And this is the approach that Hook and Marquez-Tavares took, and one that I also proposed in a different way. This makes use of the axions coupling to gauge fields in this that we saw earlier as well. And this coupling has also been used in a different way in the n=1 models. So in these papers, they use them, for example, to have additional friction during reheating, so the relaxon doesn't roll past the weak scale, or in the second paper as a way to reheat using particle production. But this was all within the framework of the original GKR mechanism. So what I want to propose is basically that particle production can inherently be a part of the backreaction mechanism if it depends on the Higgs vacuum expectation value. So in the mechanism that I proposed, it was essentially taking the original GKR mechanism and just making it completely Higgs Vev independent in the relaxon sector. So you have a very minimal relaxon setup in that it's the same Lagrangian that you saw before. In this case, there's no Higgs Vev dependence. But if for some reason inflation ends when the Higgs gets a vacuum expectation value, then what happens is Hubble will start falling. And as Hubble falls, it falls below the dissipation threshold of this gauge boson. So the relaxon then dissipates into gauge bosons, and the additional friction will trap the relaxon close to the weak scale. So in this case, since the periodic potential barriers are always on, the relaxon just starts with enough kinetic energy to overcome them, and you just need a reason why additional friction comes in and slows it down. The parameter space, unfortunately, is very similar to the original GKR mechanism, so though it doesn't have the same problems with the QCD axion and so on, it does have the same parameter space where you can see the E-foldings are also exponentially long, and the cutoff, on the other hand, can be raised much higher than the original mechanism. But in the meantime, there was also this paper by Hook and Marquez-Tavares, which proposed using the gauge field dependence as being the electroweak gauge fields. So in this mechanism, the electroweak gauge fields themselves depend on the Higgs Vev, and in this case, you start in the electroweak symmetry broken phase. So the Higgs mass is very large and negative when the relaxon starts rolling, and that means the gauge bosons are very massive. As it rolls, it goes down and the gauge bosons get lighter as the Higgs Vev gets smaller and smaller. And at the weak scale, you see in the equation of motion for the gauge bosons here that when the Higgs Vev is small enough that the gauge boson masses falls below this threshold, the equation of motion has a tachyonic solution that exponentially produces gauge boson modes. So this exponential production of gauge bosons switches on at the weak scale and provides a trapping mechanism that is very efficient. And in this case, the parameter space can be very natural. So the parameter space for these models can be sub-Planckian, so the field range is no longer super-duper Planckian. You don't have exponentially long E-foldings. They can all happen within a Hubble time. And you can even do this after inflation. So the relaxon can start rolling after inflation. So if these models are to be a realistic cosmological model, then we also have to start thinking about other issues, such as how do we do leptogenesis or baryogenesis and generate the matter-antimatter asymmetry. And this is what we proposed in the relaxon mechanism with particle production. In the original GKR approach, people pointed out that the difficulty of realizing baryogenesis was just another reason why these models were a bit too unnatural, even if the Higgs mass could be naturally set. In the original GKR model, as I said, inflation has to be at a very low scale. That restricts everything from the reheating temperatures and the fact that you can have no new physics below the cutoff. But with the cosmological relaxation and with particle production, you can have the particle production reheating the universe. And while it reheats the universe, you can do leptogenesis in a very minimal way by using higher dimensional operators to generate your CP violation and lepton number asymmetry. So this is a mechanism that, for example, Hamida and Kawana proposed, as well as Nicole Bell and others. And the mechanism doesn't introduce any other scalar to do the matter-antimatter asymmetry. It doesn't introduce any low scale fermions to do lepton asymmetries from decays or anything like that. You just take the standard model plus the higher dimensional operators at some cutoff with the relaxon Lagrangian and the same terms that we saw before. And this is enough, we say, to do the lepton asymmetry. What happens is that when the relaxon is rolling, it also couples to these fermions. And I didn't mention before, but this coupling to the fermion current is necessary to allow the relaxon to decay from its thermal abundance. So the relaxon will have some thermal abundance, and it needs a channel to decay to not be overabundant. So this coupling is also natural. It respects the shift symmetry. And it necessarily means that leptons will be produced as the relaxon rolls and produces gauge bosons as well. So as it's reheating the universe, it's also producing leptons that are out of equilibrium. These leptons that are produced out of equilibrium will scatter with the leptons in the thermal bath via these diagrams here. So these will be mediated by higher dimensional operators, and the interference between these two diagrams gives you an asymmetry. So if you calculate this and do a rough estimate of the baryon asymmetry from this reheating era leptogenesis, then you find that for a scale of 10 to the 5 GeV at the natural cutoff of a subplanckian relaxon mechanism, you can generate enough matter-antimatter asymmetry. So this parameter space points towards heavier axions, towards 100 GeV, or even heavier possibly. You can also have lighter axions for other parameter space regions. And the decay constant of the axion would be around 10 to the 7, 10 to the 8. And in this case, we don't have any extremely small numbers, so the shift symmetry rating parameter G is about 10 to the minus 8 GeV. The interesting, conceptually attractive view of this approach to me is that if you tie leptogenesis to the relaxion, in the sense that the relaxion generates the matter-antimatter asymmetry, then this combines the dynamical selection mechanism of cosmological relaxation of the weak scale, which dynamically selects a vacuum where the weak scale is small, to a censorship type approach, which tells you that we have to live in a universe where the weak scale is small, because otherwise we wouldn't have enough matter-antimatter asymmetry to be here. So this is conceptually similar to, if you've heard of naturalness models, where in their case the inflaton reheats to many sectors, and it only reheats to the sector with a small weak scale. In this case, we only live in a dynamically selected vacuum that has the right initial conditions for the relaxion to generate enough matter-antimatter asymmetry that is correlated with a small weak scale. So there are many directions to pursue, and cosmological relaxation is not a full solution to the hierarchy problem. It's saying that maybe in the early universe, if you have this set up in a certain way, then a scalar can naturally relax the weak scale, but it doesn't explain up to the Planck scale or up to even the gut scale the solution to the fine-tuning problem, and it doesn't give you an origin to the electroweak symmetry breaking potential, so that is still expected to come from some other sector. But now it can be decoupled at a higher scale, and we expect UV completion, which would be the typical supersymmetry, composite Higgs, or extra-dimensional model building. So you can see some papers there from people who have pursued this direction. So far, only with the n=1 GKR models or the n=2 double scanning mechanisms, but I think there's still scope to supersymmetrize the particle production models and find if there's any non-trivial phenomenology that comes from combining the two there. There's also been attempts to rescue the original QCD relaxon, for example, the paper by Nelson and Prescott-Weinstein. Basically overcomes the problem with the CP violating minimum by having an effective temperature that suppresses the QCD barriers during the relaxation, so that once the temperature goes away, the barriers go up, and then the new minimum preserves the the CP conserving minimum. And then I think there's still scope for many other scanning and trapping backreaction mechanisms, in that there are many Higgs-dependent phenomena in the early universe that can be used, not as a way to do cosmology, but for cosmology to set the weak scale. So the phenomenology of these models is also something that has been looked at in the past for these n=1 models, and I was going to say that particle production is still something that hasn't been investigated phenomenologically in terms of cosmological signatures, but just today I just looked on the archive and saw that Anne Nelson, Geraldine Servant and others did a paper today exactly looking at the phenomenology of relaxation with particle production in detail. Okay, so this was a very quick overview of why I think the hierarchy problem is now an even bigger problem than it was before, in the sense that it's the same problem that's always been there, and it's even worse given that we haven't seen anything at the weak scale. So rather than saying that the problem was never a problem, I think that the problem has other solutions we haven't thought of, and cosmological relaxation is a way to think about the problem in a completely different way to how it's been done before. It's maybe been dismissed prematurely based on the original models, which I think are more proof of concepts rather than realistic models. And I try to emphasize that there are still many other Higgs-dependent phenomena that can be used to maybe have different ways of doing the scanning and the back reactions and so on. And relaxation with particle production is the closest step towards that. Thank you.